I'm assuming some more people will be coming once Angeles starts speaking, right?
Yeah, I think so.
Today's presentation, Kent seminar, we're going to talk about, give an update about one of the existing ICT projects. Anjali Yames and Songu Kang will be making the presentation. I think everybody knows them. No need for an introduction. They are both PhD candidates, right? Candidates, almost finishing their PhDs. And they have been helping me in this project, and I think it's a great project. They will just, it's a different kind of project. It's not a research project, so don't expect to see very fancy results, simulations, and anything else. But there are more practical things that is going to be presented today. It's about the training material that we have been preparing for IDOT, for their rehabilitation and preservation practices and their manuals. So without further ado, let's give them a warm round of applause and then get them started.
Good afternoon, everyone, and thank you, Dr. Zer, for giving that nice presentation. And as he mentioned, this project is it's a different spin with what ICT is used to. And in particular, when we started this project, what we wanted to showcase are the materials that IDOT engineers or planners are going to learn in order for them to do a proper rehabilitation program or create the strategies. But as we've gone through the materials and also have had the opportunity to talk to many districts and through our TRP meetings, we really started learning a lot regarding IDOT and their rehabilitation. Thus, the title of our presentation are the realities of rehabilitation for pavements. And specifically, we're going to focus on the case studies that we've gone over here in Illinois. First, in a general scope, as we know, the amount of new construction that we're doing with respect to pavement structures has declined a lot relative to the projects that we need to preserve and rehabilitate, just because of the fact that today we have a big, extensive network. And that's one, to meet the increasing demands of consumers to get to and from places or get goods, but also there has been a coincidental limited budget. And as we know, in order to meet this demand, or along with these demands, other things that we have to take into account when we're preserving or rehabilitating our pavements are the corresponding climatic conditions, traffic load, and volume. And in essence, for us to create an effective preservation and rehabilitation system, what we really wanted to showcase to the students is we really want to create an extensive arsenal in terms of the tools and the databases and the procedure, the protocols that they must have readily available so they can select the right tools. And sometimes selecting these right tools pertaining to preservation and rehabilitations could be even more difficult than design because of the complexity of the problem. And in particular, to bound our main question of do we preserve or do we rehabilitate, for the main key things that we have to take into account, obviously the pavement condition in terms of severity, frequency, the governing distresses within that pavement section, the traffic, what's currently going over that pavement section of interest, but also the future traffic that we are anticipating. Another limiting factor is the technical feasibility. We have to stay true to what's available locally and also what we can do. And last but not the least, very important is the budget. And so these key factors really help us determine, do we preserve and rehabilitate, and to what extent do we do that? And to complete this task, we want to complete two main objectives. One is to preserve the pavement investment, meaning we want to minimize the structural failure that we're encountering, and also extend the pavement life by preserving and in terms of the functionality of the pavement. And alongside this, not only do we have to preserve the investment in terms of monetary, but we want to ensure that the main users, road users, including every single person in this room, is to be able to experience an acceptable level of service in terms of smoothness and friction and so on. And so if we are able to understand how, understanding pavement distress evaluation by one, identifying the distresses itself, the type and severity and so on, identifying do I require some testing to understand further what is the governing distress that I need to fix, but also the feasibility of treatment. So if I'm able to work these three important components, then hopefully at the end I'm able to apply the right treatment to the right pavement at the right time. So at the end of the day, the main umbrella that we want the students to learn in this class is to really feel confident that, one, they have all the tools and the protocols and the methodologies that they need to be able to identify that right treatment for the right pavement at the right time. And as a big picture of how the guidelines are showcased, as we anticipate, one, the first bounding parameter is to identify the pavement type. That alone will filter a lot of our tools that we can use. And based on that, we will define the prominent distress. So maybe we have 20, but at the end of the day, what we want to hone in are critical distresses. In particular for the CRS, there will be 5 major distresses that we want to fix. And based on that, we want to tie that into the required or anticipated level of service in terms of the traffic that we're anticipating. And hopefully, we'll be able to create a list of potential preservation techniques that will be balanced with budget limits to really select that optimum preservation techniques. But with respect to preservation, the main caveat of applying this is the pavement has to be structurally good, meaning we are only of interest to fix the functional distresses of our pavement. Now, if we surpass that point where it's no longer functional, but it's also structural, now we go into rehabilitation where it not only addresses the surface failures, but also the structural failures. And these functional and structural will have a better definition later on, but just as a big overview of what rehabilitation. And as we can see based on this graph, when we have a decline in the condition, our main interest is near this midpoint or the midlife of our pavement structure, where we want to address not only the severity of the distress, but we want to properly diagnose those distresses, and again, bounding those with what's feasible to do for that approach, and also the cost, putting the reality to this distress and how to fix it. As I've mentioned, here's a brief overview of the difference of structural and functional. For structural, as we can anticipate, this deals with the load carrying capacity, and if we have lost that, wherein our pavement can no longer sustain traffic loads, oftentimes that is tied with pavement damage, with the pavement layer itself, the main layers on top, or the foundation, so deeper into the pavement past the surface layer. On the other hand, for functional, this generally it is generally describing the surface deteriorations, so how a person's rideability, riding experience on top of a pavement, so with regards to roughness. However, this typically is not constrained only to the surface. As we know, like distresses often evolve over time and it worsens, and functional generally or can turn to structural failures. And here are some examples of distresses where we see here fatigue, distress in AC pavements, decracking in concrete, and for functional, a localized pothole where we can see here, or polished aggregate, which we tend to be concerned because now our safety as we're traversing that pavement is influenced. Now, with regards to identifying or characterizing the distress, not only one, we have to identify the type that's related to the pavement itself. We also have to define the severity of that distress. Is it low, medium, or high? Or with a CRS, it ranges from 1 through 4. We're not going to present the CRS entirely, but just to give you an indication of how this is done by IDAT. But also, with a severity that's often determined by the crack width, not for all the distresses, but some of them, the area that's affected, and what type of distresses are present. With regards to the extent, in the CRS rating, that coincides with the frequency of the distress along the section of interest, and all this are taken into account by this metric that they use to track the progress of their pavement deterioration, or with the application of rehabilitation, how their pavement condition is rated through this condition rating survey. So as a brief overview into the CRS, they do have a class. They take a class, an extensive class for the employees to be raters, because this defines which pavement structures become critical to be fixed, and how do we describe them. So what they do is they start with a collection of data. This can be automated, not automated. Automated in terms of there will be a vehicle passing in a network level. So what they do is biannually, they move from one direction then to the other direction and collect data. And they collect data through pictures and also video of having a front camera and also downwards camera. And so the idea is for them to take pictures and database of these distresses, and their, I think Road Vision is the name of the software, and we'll go in detail later on, but pretty much is to have this automated process of characterizing the pavement condition itself. And based from that, you can identify undistresses from that data. And also, we've stressed prior that not only do I have to identify the type, but also put some metrics on those distresses in terms of severity and extent. And at the end, use their guidance to have a single value distress code to assign that, okay, this pavement is bad, but it's bad by this CRS value. And just as a sample of how CRS is assigned for a section, what we're considering here, so for instance, in a given project, we assigned a 1 mile CRS rating section. And what we collect are the IRI value, the RUP depth, and the faulting data. And each value is collected in an increment of 0.1 mile. And at the end, what happens is at every increment of these data collected, we take the average, and that becomes one of the inputs out of the 6 to get the CRS value. And these 5 prominent distresses comes from a list of tables of fatigue, different types of centerline cracking, and it's identified by a letter, which is corresponding to a type of distress, and also the level and frequency. So when I said 1 through 4, as it increases the number, the severity increases, and then when it switches from 3 to 4, usually that delineates the frequency between the distresses. And so by following this simple schematic of how the CRS value within this section that we assigned, we get a single CRS value. Now going to the backlog, or actually regarding the CRS, as I've said, this is a rating value, and what they do is they rate from 1 through 9. So that final value will be from 1 through 9, where 1 is the worst and 9 is the best, and 5 is in the middle. And you'll see in this diagram that we got from IDA in 2017, some of their threshold levels were they try to identify when to characterize that section as a backlog, which means, as we define here, a backlog is a pavement condition to where an improvement is recommended now. And so when you even go further down or below that CRS, now it becomes critical, where the associated cost is significantly greater due to the severe deterioration of the pavement. And here's an example. This is US 45 prior to the project that we observed this past summer. And Sunggu actually got these pictures from IDAT, right? We took them, sorry. So during that evaluation, we also saw some of these stresses. This is one of the joints. You can see the past patch severely deteriorated, and Sunggu rated this as below 4. So just an example of a section that has that CRS rating. And so with that CRS data, as I've mentioned, a vehicle travels throughout different networks of IDAT, and that's the network level data, where, thank you, Sunggu, where, as I've mentioned, that data collection vehicle obtains the videos to provide metrics on the running, IRI, and faulting. And as I've mentioned, this is done annually, one direction first year, and then the next direction will be the next year. But another set of database that's really important when we try to create a decision for what rehabilitation we must do. Another database that we can rely on is additional investigation, which focuses on our project level data. Now with this one, it takes into account the use of destructive and non-destructive testing, where it really hones in the metrics in terms of deflection, material characteristics layer, and really characterize that section itself. And some of the useful information that the project level data could be used is, one, it could be integrated to the network level decision making. We are able to provide a detailed crack mapping of the stress, define structural capacity, load transfer, foundation, and thickness. And as I've mentioned, it also includes destructive and non-destructive testing. Now, I do want to disclose that this is not done for every project, but the main idea is this is available to be done, or at least to be explored by IDOT engineers and planners once they learn this class. And for destructive, what they typically implement is coring, and for the non-destructive, there's FWD, GPR, which we're very familiar about. And typically, this data collection, since we're honing into the specifics of this project, is typically very slow. But then we're gaining a lot more information. And just some of the pictures of the testing that I've mentioned previously. Here's the FWD, the skid friction testing, and the DCP, and also the GPR. And I'm going a little fast on this because the most important part of this presentation is actually what Sanggu will be presenting, which are case studies in Illinois, trying to implement the steps of getting a rehabilitation options for our pavement.
Thank you, Anjali. I just discussed about the basic introduction for the rehabilitation and preservation. And right now, from this part on, I'm going to present some case studies which actually shows the real case or real rehabilitation practices they do in the field. So we are actually going to have two case studies. The first one is about rubblization, and the second case study is about the typical resurfacing. And I'm gonna start with the first one, which is on which happened in the city of Monticello, Piatt County, and this is actually county highway, which is 5 miles long. And what we do in this case study was to diagnosis and then rehab design for this existing pavement. So for this pavement, which is actually starting from here to the end, which is 5 mile length, near city of Monticello. And just to give you a brief overview, this diagnosis and the rehab design was actually contracted by SAA to ERI, and ERI is part of the research team that we are working on in this project. And one of the objectives in this project was to actually evaluate the structural capacity of the existing pavement and come up with the possible design alternatives. And then to do this, ERI actually implemented several different testings, including destructive and non-destructive testing, including coring, non-destructive testing, including GPR, as well as falling weight deflectometer, FWD, as well as some automated pavement distress surveys that actually took pictures of the real pavement sections. So this section that we have in the case study 1 is actually PCC pavement, and the first 0.5 mile is actually pavement slab size 5.5 feet by 5.5 feet, and first 0.5 mile is actually with these slab sizes, and then rest of the 4.5 mile is actually 11 feet by 11 feet, and it's actually bigger, twice greater than, 4 times greater than the previous section. But this type of pavement is actually white topping because they actually overlaid PCC on top of existing AC. So it's unbonded thin concrete overlay, which is actually white topping. So although it was it was a county road, it has a lot of traffic, relatively high traffic, which is about 2,400. And one thing that we have to notice is that it has actually pretty high truck traffic, which is 6.7, around 7%. So it's, I'm gonna talk about what the significance of this traffic later, but first move on to the cross-section, existing cross-section. As I said, this white topping PCC overlay is only 5 inches, and it's actually sitting on top of the existing AC overlay. And the problem of the pavement was actually, it was experiencing a lot of structural distress, including longitudinal cracking, corner breaks, cracking near the edge, as well as shattered slab. And these are very severely deteriorated, and it was actually happening throughout the length of the pavement. So pavement condition was pretty bad. And this is some of the pictures that one of our research team took actually in the field. And this is actually showing the corner break and some of the images taken from the vehicle. It shows the longitudinal cracking in the mid slab and edge crackings and some of the corner breaks, and very severe longitudinal cracking along the pavement slab, and also corner breaks and shattered slab. And these are actually happening through the entire length, and it's very deteriorated pavement. So what we actually, so the research team, ERI, actually started with the destructive testing, coring, and then they took cores at many different locations as shown. And from this, they found existing pavement structures, but also they found the condition of the pavement. But doing coring is actually very costly and time consuming. So they actually moved on to GPR to find the continuous, the depth of the pavement structures. So what they found was a pretty constant depth of PCC. Below, they have one lift of AC and another lift of AC below it. So like adding them all, its entire pavement thickness is about like 10 to 11 inches. And also what they did was the FWD. They wanted to find the maximum deflection of the pavement to find the structural integrity of the pavement. So this is one of the results they got. It's actually varying a lot. And one thing that we can get from this picture was that there's weak point and the strong point in this pavement section by looking at the maximum deflection from FWD testing. And also what they did was the % load transfer efficiency. So, and as a result of FWD for LTE, they found that most of the load transfer was above 80%, which is pretty adequate. But some of the cases, some of the spots, they experienced very low load transfer efficiency. That means it might have some localized problems there. So from the FWD results, as I mentioned, the maximum deflection was varying a lot, and there's weak and strong areas along this pavement section, and also overall load transfer efficiency was also measured, and back calculation based on the FW measurement was done by using in-house software by ERI to calculate the modulus of the pavement structures. And what we learned from this testing was that the coring actually shows that the concrete layer, the surface concrete layer is actually under 5 inches, which is actually a little lower than the design thicknesses, and which cause problems because, as we mentioned before, the traffic of this county highway was pretty high. So if it was under-designed and traffic is higher than expected, then pavement will, of course, fail, right? So as well, they also conducted the dynamic cone penetrometer DCP test, and then the Illinois bearing ratio was actually below 3, 2.85, indicating that subgrade soil is very weak. And GPR analysis actually confirms the coring results, since we saw that the concrete thickness is below 5 inches, and GPR actually shows the same results as well. And FWD, we actually evaluated most of them above 80, but some of the localized failures due to from the low load transfer efficiency. And as a result of this case study, we can actually, just to summary of this case study, concrete layers were very structurally deteriorated based on our visual inspection and other surveys that we conducted. And the structural capacity of existing pavement is deficient because it was designed lower than what was actually supposed to be for the traffic. And the distress was actually present for entire section. So it actually had to have some structural improvement for rehab. So finally, what ERI came up with was maybe 3 different solutions. And the first one was patch and overlay. And depending on the severity of the distresses, maybe some locations were full depth patched, and then on top of that, they'd probably do the structural overlay. And another alternative was to reconstruct. So that means remove the existing pavement from the top to bottom, and then just place another new PCC pavement up at that section. And then the third one was more sustainable option, which is rubbleization, that actually rubblize the existing concrete pavement and use it as a base course. And then on top of it, you have a AC overlay. So these 3 alternatives were considered, and at the end, I think using IDOT modified AASHTO design, rubbleization method was selected. And then I actually visited the site, and it's in very good condition right now after they do the rehabilitation. And the second study was actually about the resurfacing of the AC pavement. And as you can, probably you drove a US 45 from Champaign to get here too. But it's between Urbana and Tomasboro instead of Rental, because between Rental and Tomasboro, it was already rehabilitated 2 years ago with the resurfacing. So in this, this highway was 2-lane divided highway, and it's about 5 miles long. And 5 miles long for the rehabilitation. And both southbound and northbound was rehabilitated. But before rehabilitation, the level of CRS was actually 3.9 based on the record they have. And it actually belongs to the critical backlog that Anjali explained. And as you can see, it's in Illinois, and then the section that was rehabilitated is shown here. And the problem of this pavement, as I mentioned, CRS was 3.9. As you can see, it's very deteriorated pavement. A lot of block cracking, longitudinal cracking, center line cracking, transverse cracking. And if you actually zoom in, this is one of the areas where they patched before, and the new patches here. The transverse cracking, reflection cracking is very severe. And also a lot of cracking as well as raveling. The very high severity raveling surface distresses actually creates a lot of problems in this pavement. And most importantly, the center line cracking of this pavement was really awful, as you can see from here. So if you look at the cross section of the pavement, the old existing pavement actually had 2.25 inches of AC on top of 3.75-inch AC, existing AC. And below that, you have a PCC pavement of 10 inches. And what they decided to do was to mill 2.25 inches and then place 0.75 inch of leveling binder plus 1.5 inches of surface course. So pretty much top 2.25 inches were milled and replaced with the new overlay. So actually, as far as we know, there was no destructive or non-destructive testing was conducted by the contractors. So our research team at ICT conducted many different tests during this summer to understand the pavement. And one of the things that we did was a visual inspection. We actually have the record of CRS, but we actually wanted to go out in the field and actually see the distresses by ourselves. And as we show in the picture, the distresses that we saw was actually matching with the CRS documents. And so we actually confirmed the CRS value was reasonable for this section. And we actually saw the process of partial depth patching when they were doing it. And with the help of Isam and Mike, Hassan and Anjali, of course, but we actually did the FWD testing for this pavement. And with the help of Shannon Shichi and Mike, of course, we did the GPR measurement for pavement thickness. So this is a picture of partial depth patching where actually they did it in the reflective cracking area. So they actually milled this area right here and then clean it a little bit and then apply this tech coat on top of it and then put the AC patch material and then compact it with the compactor. So this is what they did for the partial depth patching, and they actually did it a lot along the length. I think maybe 20 or 30 partial depth was done throughout the length for both north and southbound. And we also did the FWD measurement for the pavement along the slab, mid-slab, as well as along across the different cracks or joints, so to see the differences. And this results is actually showing how bad the pavement is. So before patching, if you look at the left-hand side, we have a deflection basin like this for the mid-slab. So it's regular shape deflection basin for FWD, as probably know from the class, right? And but if you can see this one, this was across the joint, and we can see that the deflection is very high for this section. It actually it indicates that there is no joint load transfer in this area, because the holes, both of the slab actually deflect, it's actually one of the slab is actually deflecting a lot where the load is applied. So it actually shows that there's no load transfer efficiency is a big problem for this pavement. Also, after patching, you see the similar behavior in the mid pavement section, and then, but joint deflection is actually increasing a lot where the load is applied. It's because I talked to Isam, and it's because after patching, there is a soft HMA material, and when we apply the FWD on top of it, there's maybe more deflection at the soft materials. That's why we see a lot of deflection as compared to mid-slab deflection. And also what we did was GPR measurement. So not only we did the GPR measurement, but we also did the coring to validate the GPR measurement. And some of the results that we got from GPR measurement is actually showing that this is pretty much 0-inch AC. This is for the thickness of the AC, surface AC, after milling. And this is actually varying from, which is 0 inches to the 2 inches. So this is 0 and this is 2. And it's actually varying a lot along the distance. This is about like 1 kilometer section. And we can see that the thickness of the AC is varying a lot with the distance. And this is another section, and this is varying a lot from 0 to 1.5 inches. But one thing that we actually are not sure about is the design. We actually compared this data with the design manual, with the design contract documents. So from the design contract document, it was supposed to be maybe 4 to 5 inches AC should be remaining after milling, but we actually found very thin thicknesses, which is below maybe 2 inches. So this is one of the findings that we had from this trip. But I don't know why, but it just, the measurement is actually showing very thinner AC thickness. So this is actually for the concrete, and concrete layer is actually very constant through different, through the distance, but then it's actually a little lower than the design thickness as well. Maybe this is the green line shown on the graph on the left, and on the right is the 10-inch, and it was a little lower than that. So what we actually learned from this case study was that, as we saw from the pictures, US 45 was very, very structurally deficient pavement section. From the distress survey point of view, as well as the CRS. And a lot of partial depth repairs were made before milling and overlay. And also, we actually found that there is very little load transfer efficiency from falling weight deflectometer. And existing AC layer is actually very, very thin as compared to what we are supposed to have in the contract document. So this is some of the findings they've found from case study 2.
So we started from the network level of how IDOT gathers their data. Sunggu presented some really nice case studies and how they navigated through this problem. And to end this presentation, we want to share with you some interesting cases that we saw. And this is a play and No Doubt song. I don't know if you guys know, but Underneath It All, which is Underneath It All pre-overlay treatments. This one, I want to credit some of the pictures that were given by David Lippert. A really, really nice database. But first picture that we want to share with you guys are these post-milling scalps. So essentially, as you know, you tell your contractor, okay, mill this given thickness. After you mill, you really see the variability of the initial construction, or maybe the rehabilitation past that. And so for IDOT engineers, the main question is how do we navigate this variability? If we leave this, will it emanate into distresses? If so, how do we address that? Maybe another approach is going deeper and going to the bare concrete, so removing everything. Another approach is maybe just focusing on the surface layers and maybe shallower depth, and really honing in, focusing on that structural overlay, and not focusing on deeper into the pavement. So these are some of the key things that we really learned and we got to see and observe from this class. Another example is, again, after milling, you really don't get to appreciate some of these cases that are really complex and even special. So as you can see here, a joint deterioration of this continuously reinforced concrete that you'll never see really at its gravity if you don't mill. And so examples like this really provides an opportunity. How do we creatively solve this within our constraints in terms of budget and then the resources that we have? Another example is the full depth Class D patch. And actually, when we were in US 45, we had a nice field trip in terms of like locating where these humps are. And let me explain what the humps are. The difference in material property between the concrete and the asphalt layer when you're experiencing the warm weather, and people who were in 508 heard this before, but let me refresh your memory just in case you forgot. This difference in material property when it's a warm weather, your concrete wants to expand, and so this AC material will not restrict that, that movement. And so in summertime, and actually even during our drive, we were trying to look for those humps where they apply this AC full depth overlay. As the concrete is pushing, it's going to even create this hump. And so that's an issue that is emanating in reality. And the idea is how do we address this? We have limited budget. We can't really replace this with a full-blown reconstruction, or even maybe consider a concrete overlay. Right now we can do HMA. As an engineer, how long will it last, and how can I prolong my money using this approach? Another interesting scenario is addressing these transverse distresses. As you can see here, I can't tell from the picture if they grouted or if they routed, but as you can see here, a takeaway from what they did in the project is really addressed this reoccurring transverse cracks before overlay. And again, it's just an example of the different approaches and prior to overlaying. And another distress, I don't recall where it is in Illinois, but this is also provided by David Lippert. The centerline joint density is a very common problem here in Illinois. And one of the reasons for this is it's very difficult to get density over at this region. And so some approaches that you may take is one of the techniques that they're trying to implement in IDA. It's called longitudinal joint sealant, where they put that polymer base, almost like a sealant-based product on top of it to really prevent further moisture and infiltration into that crack. And what they've observed in some of their test sections is somehow they're able to get better density in this region where generally it's very hard to get, which emanates into this center line joint. And this actually, this last picture corresponds with the US 45 study that Sunggu nicely showcased today. And it's really interesting to see something like this in the field where they took a full depth milling of this AC overlay, and the hole that you're seeing on the left-hand side is literally from air blasting, which really showcases the gravity of how deteriorated this pavement, this concrete pavement is. And for this approach, what was implemented is they cleaned it and they patched it. They put tack out and they patched it. Is that the best solution? I mean, I think we can all agree that it's not, but again, given the constraints, that is how they address the problems. And really, this class is not to maybe make engineers and planners think idealistically, but really realistically on how to address distresses like this with your constraints. And going back to the network level, now let's look back at the CRS data and the usefulness of it in terms of thinking ahead of how we can preserve and rehabilitate. And what we're seeing here is a given section that was monitored from 1991 to 2015. As we expect, we see the pavement condition declining. And what we see here is a plateau of our CRS, which tells us, and we haven't, we didn't verify this, but just to provide like a schematic of maybe a possible advantage of doing preservation, even if you have a declining pavement condition, is it allows you a time delay for overlay versus if you let it go, then that time you can't save. So it's not the premise of fixing it and putting it back, but how can I prolong this so that maybe I use my current resources now before I actually have the money to overlay it and rehabilitate completely. In a different sense, if my, here's another example when my CRS is completely below the threshold. This should be in the critical backlog that we initially said, where this pavement is so bad that the cost to bring it here is going to be astronomical. But what we're learning here is even if maybe you have a really poor pavement section, you can still use maintenance activity to at least not further degrade that pavement, but hold it until, again, you have that the budget restraint freed up, so you can perform a major rehabilitation to bring it back to good condition. And bringing it to the cost, this cartoon is not representative of how we see pavement condition deteriorate, but as an example of what we have here is new construction, and we're the complete failure. And here it declines. We perform major rehabilitation, assume that it goes back to the level of construction before it complete failure, option 1. Another option is to consider preventive maintenance or preservation, where we set a trigger, and at this condition, we set it at 8. I think this is a PCI level, so it's not the CRS from 1 through 9, but it's the same idea. And where you have these multiple scheduled maintenance and repair to bring it back to the same condition, but a lot more times during that lifespan. And sometimes, though it may not be true for all cases, but the idea is reaching back to the same level of condition. Sometimes when you do major rehabilitation one time through versus doing multiple preventive maintenance, sometimes is more cost effective than doing major rehabilitation and waiting for it to deteriorate prior to bringing it back. And so for this class, one thing that we really realized is we cannot create a recipe book for rehabilitation and preservation. If you get it, I think you deserve a Nobel Prize. But it doesn't exist, and it's hard to exist. And so from this class, we believe that it's really important for statewide agencies to provide a platform such as this class of this project. So again, going back to the general philosophy that we had at the beginning is to determining or applying that right treatment at the right pavement at the right time. And Sunggu provided some case studies where there were maybe the contractor didn't perform, the FWD and GPR, and we did just to get to know the pavement more. And what we're trying to point out is maybe full-blown analysis may not be required, but it's really important for engineers to think through, and even planners, that they should really exhaust this arsenal of tools and information and methodologies to really optimize our resources and to extend the longevity of our roadway networks. And finally, Sungu has acknowledged a lot of thanks to Greg, Mike, Isam-Shan, and Sichi for the data that we collected in US 45 and throughout the needs of this project. Principal investigators, including Professor Azur, Professor Akhadi, Professor Riesler, and Professor Thompson, working with ERI with Dr. Abbas and also Jibril. And our TRP chair for this project, Charles Weinrag. And also we want to acknowledge the districts that we've talked to, and we've really collected some nice information. From District 6, it was Steve. From District 4, no, from District 4 it was Steve. From District 6 it was Greg. And from District 7 it was Tom. So we really want to thank them for their time. We spent multiple hours with them to really get to know their rehabilitation and preservation practices. And with that, we'd like to open the floor for any questions that you may have.
All right. Question.
Can you go to the last slide, the major rehab versus minor? Yeah. So my question is, major versus minor, if you rehab to the optimum condition, like the top line, and then will the deterioration rate be the same?
Realistically, no. I mean, because it's not the same pavement structure, and the overlay may be new, but the overall deterioration might not be exactly the same. And again, like, this is a cartoonish schematic of how the deterioration is. So possibly similar, but not exact.
Yeah, let me ask a question. So in US 45, you had this leveling binder, and I think there are many other districts using leveling binder, right? This is for the non-intest states. Intest states, they don't use leveling binder. So what is the purpose of leveling binder in this kind of situations in US 45? Do you think they're effective? Are they doing a really good job that they're supposed to do?
Sure, yeah. Leveling binder is something that we actually place it to make a platform for subsequent overlay on top of it. But usually it's not structural layer. It's just like making the surface so that surface flat so that we can place something on top of it. But depending on the materials and the thicknesses that you use for the leveling binder, it can be very effective, and it can be actually working as a structural layer. For example, if you are using a little smaller gradation for the leveling binder and a little thicker thickness for the leveling binder, it will actually provide some structural addition to the overlay. So depending on the materials or the thickness that we use, I think it can be a very effective way to maybe to use it as a structural layer and provide platform for subsequent overlay. Plus, it can be maybe retarding some of the reflection cracking also.
What is the Jordan, it's 3/4 here?
Right.
Any other questions?
So thank you, very good presentation, very interesting pictures. And, so I have actually two questions. Question number one is about US 45 and those properties and load transfer efficiency that you guys captured with the WD testing. So I had a question: how did you actually locate
can. So the first question, sorry, remind me.
About like how do they position the
Okay,
location?
okay, yeah. So we actually located the joints prior to the overlay. And so we went to the section specifically where we can identify the pre-patch location or the joint location, and they've actually marked those locations and the geometry of the patch. And then we use their stationing to trace it back. But I think for FWD, we trace it that way. Now, the second question is how this approach is addressing load.
That they gave for this partial level.
Yeah.
45, how did they add this load transfer efficiency?
So in terms of this application, and Sunggu can correct me or add on to this, it doesn't address load transfer deficiency. In this specific project, was load transfer the prime problem that they wanted to fix, and the answer is no. Due to the limited budget, they want to address the joint to a minimum level because the pavement is bad all throughout. And as Sunggu presented, maybe one of the approach that should have been done is to take out the asphalt layer, rubbleize it, because as you can see, even in that air-blown section, the durability is no longer there. So if we were to address a load transfer and concrete that's no longer durable, then that's not useful for how we want to fix it. So.
And also, the condition of the joint, existing joint in the PCC is already bad, and load transfer efficiency was already so bad. So there is, unless we do full depth patching or something, there's no way. I mean, they didn't actually address the load transfer efficiency for this case.
So those problems more sooner or later we're gonna see those.
I hope not, but we may.
Alright, thank you. So maybe a quick follow-up on that. What if the concrete is in good shape, just the joints is really the problem? Alright, overall concrete is in good shape, let's say the problem is only the joints. Now why would you rubbleize that?
I mean, no, in that case, then I wouldn't rubbleize. And I mean, we can explore the different types of patches that IDOT has in their recipe book. So if it's a doweled problem, then I will use the class that will fix the joint. Oh, in that case, if the problem is completely changed when you have good PCC, then rubbleization may be too much resource-wise.
So at the beginning when you were showing like the graph of the realization, and you were saying that at the very beginning you do like reservation and then the question here when we're looking at any condition and whether it is like the PCI or PRS, sometimes we have very low values, like it's within the reconstruction, but then you go and then you see that the stresses are all like maybe weather related or not low, the base are good, you don't have nothing, but it's very low. And this is actually what like I'm working on data for the campaign, and I was checking some of the data. You have a PCI of, for example, 13, which according to IWU should do a reconstruction. But then looking at what are the stresses, see that everything is in net AC, even you don't have any nothing. So how do you think this graph this graph is showing that
Sure.
with the 13 it should be reconstruction. So do you think that this is the right way?
Just to answer, the figures that we actually show like this is actually very first schematic. It's just like showing some possible scenarios, but it doesn't actually reflect the real cases in the field. But as to your question, it may be very low condition index with the very superficial distresses only, right? You said it might not have any structural capacity, structural distresses, but because of
The IDOT manual,
right.
they were saying that everything for the PCI that
Right.
below 40
Mhm.
needs reconstruction.
Right.
But I don't see like
I understand. So your question is why do we need to rehabilitate although we don't have any structural distresses because of just low CRS values, right? So the answer is, of course, I mean, it's a good indicator to evaluate the condition of the pavement, the CRS values. But it doesn't, like you mentioned, it doesn't really see the difference between like the presence of more superficial distresses or structural distresses. So that's why we need to look at the network level CRS as a reference, but we actually need to go out in the field and do the additional investigations to find the real problem is. So if we don't do that, that's a problematic. So if someone didn't do that for the rehabilitation project, I think that's not a very good practice to do. But in general, CRS value is a very good indicator for the condition of the pavement. Does that answer your question? Okay. Mike?
Sorry, this one goes way back to the beginning of the white topping on Monticello Road.
Mhm.
There was a line in there that said that it was designed for half of the traffic. Did it just not count for road, or did it have?
Oh. Yeah, it was not designed half, but it was under designed, let's say. Yeah, but maybe traffic wasn't predicted correctly, and then their design is actually under designed compared to the current level of traffic. So that's one of the reasons why the white topping is severely distressed. Yeah. Sure.
Sorry. I have a question. Regarding the PCI readings, and maybe a little bit related to what I just said. For example, if you have low PCI readings, I don't know, in the 40s, for example, which is like a poor condition according to the standard rep. But if you see it and you write it, especially, like you don't feel like it's in a poor condition. Like how well does the PCI, my question would be like, how well does the PCI reading relate to the actual experience and writability that I use for my experience? Do you think like it's very correlated, or it's more just because you have a lot of presence of distresses and structurally it's failing, but not necessarily ridership wise it's failing?
I'm not sure if as deterministic. Actually, throughout this discussion, especially from Isaac's question, now I just remember one of the slides that we have for the class is we showcased two sections, exact same CRS value, and completely different distresses, right? So in terms of is PCI a direct metric that will say, okay, if you have bad PCI, you have bad roughness. Not necessarily, right? And that's also why Sunggu pointed out that PCI or CRS are really good indicators, but to the type of rehabilitation technique that you must apply and actually what's the stress that I should address, it really requires for you to implement additional investigation and really warrant from the field survey what needs to be done. So the answer is it depends.
Yeah, so at the end you can have, as you said, you can have the same value
Mhm.
as your
Yep,
SPI,
yep,
or
yeah.
whatever, but not necessarily the experience of the rider.
Correct. Yeah, and we have that. Yes. Yep. Uh-huh.
Okay, so just to understand, all the rehabilitation technique is done based on the, surface condition, right? You go check the surface, the traffic, CRS, because you don't conduct any FWD and anything. You just make the decision based on the condition of the surface. Is that correct?
No. So they use that as a metric to monitor the pavement, but to say, okay, I'm going to rehabilitate out of this Excel spreadsheet anything that falls below 4 for the CRS. I'm gonna go. No, they don't just use that metric. That's one of their metric to say, okay, these will be in the backlog, and as we mentioned, the definition of that is it's severely deteriorated. It should be addressed now. But then they go further and say, okay, let's visit the field and say, which one of these values that we flagged really merits the rehab. No, it's not as simple as like all the 4s must be completed by 2019.
Conduct any FWD or anything to get the strength of the structure to meet the.
They do, yeah. Not conventionally, but they do. Like if a section requires further testing, then yeah, absolutely, they go through FWD. They don't go, no? The answer is no.
Coring. Maybe
I thought
IDA
they
is
do.
doing coring to see.
No, but I thought the central office has one FWD.
They only run FWD on mechanistically designed pavements. They just monitor its performance, not standard. We have treatment design.
Mm.
Those districts structural overlays. So in that case, they need FWD to get modules input. But like that, they have a recipe for two types of overlays. One is for this UGS 45 type of road, it's 2.25 inch. If you go everywhere, they include policy. If you go interstate, it's 3.75. That's typical. And they don't really require any approval, any test. Just they decide on just the section and they apply the policy. If the section is in bad shape, they have money, they go sometimes for particular overlay, but they have to get approval for that. That's how I know currently the procedure works.
I have a second question. I reserve my.
Yeah.
So, how is this is the survey being done in the States? Like a person goes and all the automatic surveying, how is this?
Right. So there is a DCV, which is data collection vehicle operated by IDOT, and actually they contracted out to companies, I think, these days. But they collect the data, the downward, as Angeli mentioned before, downward image as well as the front image. So based on that, they collect all the images of all the relevant, the highway system or the roadway, and then they can. So there are some people who can actually evaluate these sections based on the images, collected images, and also the software that process those images. They actually find the cracks automatically, and then they find the severity of the cracks and everything. So it's easy for them to identify those distresses by using those software and collected images. And there are selected people in each district, as well as the central office, so they can actually evaluate these conditions. Yeah.
Then the result of each processing is validated by the person?
No, software actually gives you all these information, and person need to decide which type of distress this is by looking at the images.
CRS is calculated by the software, but the type of distress is
Right.
decided by the person.
Yes. I mean, it is by the software.
They assign, no? It's
They assign,
subjective.
yeah, they assign the type of distress based on the collected images and the software.
But the software does not. Software gives you the images,
Right.
and then you get the ratings from the images. They decide the distance, they decide
Right.
the severity, and they calculate the severity. Then the computer program calculates the severity if you enter all the.
Yeah, of course. Right.
Then the person decides the severity and the type of distress.
Yeah, and then
Right,
you
right.
look at the CRS at the end of the day, the number he doesn't like the number he overwrites.
Mhm.
So he gives 5, it's not 5, I know what 5 looks like, this is 4. So sometimes they overwrite, they don't listen to the trust. But the software now, the current software that they're using is very powerful. They're telling them to use the full capabilities of that software. It gives you the crack width and everything, so you can correlate that information to severity. So in probably very near future, they will eliminate this rating because the computer will tell you if they see a crack, it's longitudinal transfer, you just have to decide what type of crack it is, and then the severity level will be automatically determined.
And do you consider the 3D, the image of the person?
It's a laser. But you have images too, but they
No, laser for the illumination of the image. That's 2D.
I think we have examples of like.
But it gives you the width currently, so you know, all you have to do is check those
These
widths,
things.
and then
Yeah.
correlate that, not the diagram, correlate that to severity, so that in very near future, they will remove this severity identification, but they may still, look at the image and say, well, this is this type of crack, this is that type of crack. But this is like an image, for example, the image is processed to give you the width. This is just the raw image.
Right, raw image. And sure. Any other questions?